Okay, so we're going to start combining quite a lot of things that we understand now about mechanics. So we've got inclined planes, we've got the Suvat equations. Potentially there might be some friction in there as well. This is where we really start to sort of build up um, various components of knowledge that we've hopefully acquired. Um, so just to start off with, in that case, then I mentioned Suvat equations. I thought it'd be, well, maybe fun's not the right word, but an interesting little challenge to yourself. I know you're given all the Suvat equations in the exam and in a formula booklet, but to be honest, I think knowing knowing all five Suvat equations in itself is kind of a litmus test of how much have you actually practiced, if you see what I mean. So, although you're not required to know them all when you go in an exam because they're given to you on paper, if you don't know them all, that to me says you haven't really practiced enough because you will. There's no way you could have done enough practice and still not be able to remember most, if not all, of the Suvat equations. At the very least, the big three or four that tend to come up. So, my challenge to you is this. Um, you might forget that there's five. You might think it's sort of three or four, but there are in fact five. Um, my challenge to you is: how many of the five Suvat equations can you actually write down completely from memory? Just give yourself that quick challenge. Um, Pause the video for see how quickly you can do it, 20, 30 seconds. Um, and then unpause and we'll see if you've got them right. Okay, give that a go. See how quickly you can do them. Go. Okay, and I'm not going to just sit here in silence. I'm assuming you've paused it or just skipped over that bit. The equations in order, let me try them myself, and how often they tend to come up. V equals U plus AT. S equals UT plus half AT squared. V squared equals U squared plus 2AS. One that people tend to forget, number 2, has an alternative version. S equals VT minus a half AT squared. So really they're kind of a pair. And another one that's often overlooked, the sort of average speed times time equals distance. S equals a half U plus V times T. Okay, in my experience, based on which ones I usually forget at least, it does tend to be these two that people often forget about, but they are there. Okay, these are the 5 possible ways of relating those 5 unknown letters. Okay, so hopefully you got most of those. Just take a note of the one that you keep, 1 or 2 perhaps that you might be forgetting. Make sure you do try and commit that to memory. Okay, so with that done, let's take a look at an example question within this particular topic. So we've got now a rough plane. So we're talking inclined planes, we're talking frictions because it's rough. The angle is alpha. And in this case, we're going to be talking about something moving. It's accelerating, it's sliding for 2 seconds. So we've got some movement going on. Let's first take a note. Tan alpha equals 0.75. That's 3/4. If you remember from the previous video, you can draw a triangle and quickly get out sine alpha and cos alpha from that as well. Sine is opposite over hypotenuse, so we're talking 3/5. Cos is 4/5. Okay, go back to the previous video or do ask me if you can't remember how you get from that first line to these two. And the coefficient of friction is 0.5. Okay, this particle, it's released. So remember, released means it starts at rest and it slides down the plane. What's the acceleration? Okay, so the first part doesn't need SUVAT. First part is more about considering the force diagram. So let's draw that. The weight of this thing, do we know the weight? We don't, so it must just be mg, I suppose. Okay, and then we've got these components here. That's alpha. This is mg cos alpha, mg sine alpha. It does get a bit repetitive sometimes marking out these inclined planes diagrams, but to be honest, you do it enough times and it becomes second nature, and that's what's going to make you good at it. What else we got? We've got the normal reaction, and we've got friction going this way because the object is going down the plane. And remember what I said, if an object's moving, then the friction, we can just immediately label it as mu r. Right, because we know it's at F max. And in fact, because we know mu is a half, one step further, let's just immediately call it half r. So really that arrow should be half the length of that one, but it's not to scale. Okay, and let's see then. So what are the forces going down the plane? Because that's what we're interested in, getting that acceleration. So the force going down, we've got mg sine alpha. I often forgot to add the arrowheads to the components, but they are there. Mg sine alpha. Sine alpha is 3/5, so that's 3/5 mg. And what have we got in the other direction? We've got half r going upwards, so that's minus a half r going the other way. So we need to know what r is. So let's also resolve this direction. We've got r going up, and then equal to that going down, we've got the mg cos alpha. Cos alpha is 4/5, so that's 4/5 mg. Let's then plug this r into here. So we get F equals 3/5 mg minus a half of r. Half of r would be half of this, which is 2/5 mg. So we end up with F equals 1/5 mg. And remember F here, I'm not talking about friction. F is the resultant force going down the plane. Right, that's what I said here. Down the plane is F, and that's equal to that. So if that's the net force, the resultant taking the object down, then we divide by m, we get the acceleration, right? Because this is equal to m times acceleration. So that implies acceleration equals 1/5 g. Perfect. And in fact, that would be then what, 9.8 divided by 5, 1.96. Okay, that's our acceleration. So that answers part A. Let me then just clear a little bit of working. .96 we said. So the acceleration is, let's write it as g over 5 actually. I'll just put in brackets 1.96. Now we're being asked, how far does it slide in the first 2 seconds, right? So this is effectively a SUVAT sort of scenario, right? We're talking about something moving in a straight line, and we know the acceleration. We're going to find how far it moves in 2 seconds, and we can do that because it's constant acceleration, right? So with constant acceleration, you can use the SUVAT equations. So what are the other things we know? Do we know what u is? What would u be in this scenario? It should be 0, right? Because this object, this particle, it's released. So released means it's sort of held in position to not move, and then you let go. So if it's released, that means the initial speed was 0. Final speed, do we know that? I don't think we do. Okay, we don't know that. Time, we're given that. 2 seconds. Okay, so we know three things, that's enough. So that should be enough to get us what we want to know, which is S. Okay. So then we choose the appropriate Suvat equation. In this case, S equals ut plus half at squared, which in this scenario, when u is 0, that's great because that gets rid of the first term. So we just end up with a half times a, which was g over 5. It's not a 9, that's a g. Times t squared, which is 2 squared, 4. Multiply that out, we get 2/5 g. And if we put that in the calculator, 2/5 times 9.8, we get a distance of 3.92. So that's meters, 3.92 meters. Okay, and that's it, we've done it. The distance it slid in the first 2 seconds. So you can see how this is really, you know, the beginnings of, you know, a very large field of mechanics, where you're basically saying you're able to figure out how the real world works in some sense. I mean, it's a simplified case, but you've got an object on a slope, and you're taking into account the weight of the object, the friction going on, the angle of the slope, and if you know all these things, you don't even have to do the experiment. You can just figure out how far it's going to slide in 2 seconds. So there's a lot of predictive power in all this. I mean, in some sense, that's what the field of mechanics is. It's predicting how the universe is going to work. In this case, you know, at A level, we're doing fairly relatively simple examples, but, you know, to be fair, not necessarily that simple. Okay, let's take a look at one reminder then that I want to share with you, and then one more example before we launch into questions. So I thought I'd just sort of pepper this video a little bit with a little trick which came up in one of these examples that I'd like to remind you of. And the trick is as follows. If you know what sine 10 is, you should be able to, if I told you the value of sine 10, let me look it up actually, it's about 0.17, you should immediately be able to know the value of cos 80. Reason being that they are equal, right? Similarly, sine 20 equals cos 70, sine 30 equals cos 60, and hopefully you're seeing the pattern. Okay, the pattern being namely that the two numbers in each case, they add up to 90, right? So if we write this as a general rule, I'm going to say sine of theta, that's going to be equal to cos of, and then what would I have to put here so it adds to 90? Would be 90 minus theta. And this also works the other way around. So cos of any number is equal to sine of 90 minus that number. Okay, but the way I tend to remember it is simply, if these two numbers add to 90, then it's equal, right? When you've got cos on one side and sine on the other. And this does come up, and it is quite useful. I mean, for one thing, for example, it's useful for remembering the fact that sine of 60 and cos of 30, they're both root 3 over 2, right? So really, you only have to remember half of the key values, if at all. And this is also, I mean, this is not like just a simple case for small numbers. I mean, this will literally work for anything. So let's say I had sine of, I don't know, minus 200, and I had cos of 290. They would be equal. I don't have to check it on a calculator. I know they're equal because these two numbers, they add up to 90, right? So it's a very useful little rule, and you should just, you know, remember it. It's a very, you know, quick little trick to remember, but it is useful, and it does come up sometimes. The actual justification for it, I mean, perhaps you know, perhaps you don't know. You can think about it for a moment. The justification is simply that if you take the sine graph and you shift it by 90 degrees, you just get your cos graph, right? And that's worked for every single possible value. Even though I haven't drawn the complete graph, I mean, it's infinite, it works at every value. So that's all this is really saying. It's saying sine and cos are actually exactly the same function, just shifted by 90 degrees. okay, which is why we can do this rule. Okay, so that's my little reminder of that trick or lesson, I suppose, if you didn't know it. And I think I've chosen this because it now comes up in our next example. It may or may not, but I've thrown it in there anyway because I think it's a useful rule. Okay, right, so final example before you do some questions. 2 kilogram box. It's on a rough plane, horizontal force going on, inclined by 10 degrees. You're given the coefficient of friction. Find the acceleration. Okay. So let's do our inclined plane. Put on the info. It's 10 degrees. I'm just going to draw the box as a circle just to make things simple. 2 kilogram mass. That's 2g. It's pushed up by a horizontal force of magnitude 25 newtons. You might see that in the book as a force drawn like this, because that's sort of pushing up the plane. But it does specifically say horizontal, so you've got to be careful. You don't want to draw it as something like that. Okay. But I'm also just going to draw it this way because, as I said, I prefer the tail of the arrow to be on the object itself. That's 25. Coefficient of friction, 0.3. Find the acceleration. Okay, let's do components of forces. The weight components, that's 10 degrees. That's 2g cos 10. That's 2g sine 10. And then this 25 newtons force, let's split that into components. So we've got a component going up and a component going perpendicular to the plane. What's that angle? Well, that angle there quite clearly should just be the same as this angle here, right? Because you've got the horizontal and the parallel to the plane. So that's, again, 10 degrees. So what do we get? We get 25 cos 10. Oh no, sorry, I'm labeling that on the wrong place. That's the 25 there. This part here, that's 25 cos 10. And this part here is 25 sine 10. Okay. And we then want to find the... Right. Okay, we still need to think about the resultant force as well. We haven't mentioned that. Probably need to think about that. And the friction, right? We haven't done that either. So we've got the resultant R, and we've also got the friction going this way. And remember, friction in this case is going to be F max. That's mu times R. So I'm just going to label this as 0.3 R there. Okay. Cool. So we've got all forces are either parallel or perpendicular or been split into those two components. Okay, let's resolve. So resolving upwards, I have 25 cos 10 going up. That's that one. I've also got 2g sine 10 going down. So remember, we should always put these arrows on here actually. It's a bad habit that I forget to do that. Because these components, their arrows should follow the same path as the original force, right? So if this is going down, this is going down and then across like that. And if this one's going right, then this is going up and down like that. Okay, so we've got 25 cos 10 up, we've got the 2g sine 10 down, so that's minus. And we've also got the minus 0.3r. Okay, and then resolving perpendicular, we've got r going up, that's that one. We've got 25 sine 10 down, and we've got 2g cos 10 down. So let's put those there. And in fact, I'm just going to equate them instead of saying equal to 0. I'm going to say the r going up is equal to the 25 sine 10 down plus the 2g cos 10 down. Okay. Oh, and in fact, you can see now that this must be why I was thinking about the rule, because sine 10 and cos... Oh, no, never mind. Don't worry about that. Okay, so you can't use in that case. But we've now got r. We could substitute that into here, and we could then get our resultant force. Yes, we could. I should really have written here, this is equal to 0. I forgot to note that. No, sorry, what am I talking about? No, it's not equal to 0, is it? No. That's equal to F. That's equal to the resultant force because it's moving. I don't know why I thought 0. In the second case, r minus this is equal to 0 because it's not moving perpendicular to the slope. But in this first instance, this equation, it is moving. So you're going to get some value out of these three, and it's going to be F. It's not going to be 0. Okay. Right, so we're going to have to, this is going to be quite long, I think. We're going to have to plug that value there into here and do a bit of rearranging. What's the best way to do? I'm gonna do a little bit of a shortcut here to make this easier on myself. I'm gonna say capital C equals cos 10, and I'm gonna say capital S equals sine 10. And the reason I'm doing that is to just save having to do too much working with functions that keep cropping up the same. And then let's I'm going to rewrite this as the force, the resultant force equals 25 cos 10, that's big C, minus 2g big S minus 0.3r, and r is equal to 25 big S plus 2g big C. Okay, so to be clear, this is not something that the book does or anything like that, but it's, I mean, you know, maths is a creative subject. You can do whatever you like, really. And I've chosen to do that substitution so that I don't have to do as much rewriting of the same thing over and over again. So let's say then F equals 25 big C minus 2g big S minus 0.3, and then R, which is 25s plus 2gc. So that's going to be, let's actually write here 3/10 r is equal to, what's 3/10 times 25? 7.5. So that becomes 7.5. It's a lot of working, this one. 3/10 times 2g gives me 6/10, that's 3/5. Let's not mix these decimals and fractions, actually. 7.5, that's 15/2. Okay. Right, so now I can say, taking away the 0.3r, that's 15/2 big S minus 3/5 g big C. Okay. And the acceleration then is going to be that divided by the mass, and the mass was 2. So the acceleration should be equal to 25/2 times the c minus g times the s minus 15/4 times the s minus 3/10 g times the c. And that's me just dividing by 2 because f equals ma and m is 2. Right, I'm just going to type that in the calculator and hopefully that does give the right answer. Yes, it does. Thank goodness. Okay, so that's equal to 7.06, roughly speaking. Okay, so all I did was I put that in the calculator, and wherever there was a big C, I wrote cos 10, and wherever there was a big S, I just wrote sine 10. Okay, maybe I didn't need to do that. I guess I anticipated a bit more rearranging, but we only need a number in this case. If you were actually asked to find the exact acceleration and put it all in terms of cos 10 and sine 10, then you'd have to start collecting all this together and making the fractions the same, at which point maybe doing something like this substitution would be helpful. Okay, it's a bit of a shame. I think that this example, it's a very important example. It's just a shame that towards the end it just becomes a lot of algebra, which isn't as interesting as the actual problem solving aspect of it, but never mind. Make sure you're able to come to that answer, whatever method you do choose to use. Okay, you don't have to have done it the way I did it at all, by using the CNS thing, but you do want to be able to get 7.06. Okay, cool. All right, let's try and do some questions ourselves then. How many do I have? I've got 3 questions lined up. Okay, so this one first. Boy going down a slide. Slide is inclined. You've got the coefficient of friction between the boy and the slide. Don't ask how they figured that one out. And then modelling the boy as a particle, as you do, can you find the acceleration of him and the speed when he gets to the bottom of the slide? That part B, that's where you're going to need to use SUVAT. Okay, give that a go. Pause the video now. Okay, and there is your answer. There's his acceleration, and there is his speed. Okay, second question out of 3. Rough plane, particle on it, and you're going to figure out a few forces, and then you're going to figure out how far it moves. You're going to find the coefficient of friction based on the fact that it took 2 seconds to move 4 meters. That's enough information to find the coefficient of friction. Give that one a go. Pause the video now. Okay, and there's your answer. Relevant force, coefficient of friction, 0.24. And let's get ready for the final question. Right. So, particle released from rest on a rough slope. You're given alpha in terms of tan. You're given the speed after 3 seconds. Now work out the coefficient of friction. You can pause the video now. Okay, and there is the answer. That is the coefficient of friction. Hopefully you got that. 0.180 to 3 significant figures.